Okay, so if we look at the noble gas notation for chlorine, it's got a 3s2, 3p5. There is no way it wants to give up one electron. It would really like to gain an electron. So it's got the second highest ionization energy in its entire period. The only thing that has a higher ionization energy is a noble gas. Because remember, a noble gas is what everybody wants to be. So noble gases aren't going to give up any electrons. They're not going to interact at all. They're not going to give up. They're not going to gain. So they have the highest ionization energy in their period. Does that make sense? Okay. A few people look kind of shaky on that. Okay, so in general what we say is that the ionization energy tends to increase across periods in main group elements. So let's practice this. Get out your periodic table. You've all got it out. Good. I'm going to name two elements. You tell me which one has higher ionization energy. Jot it down. I'll give you two elements. You jot them both down. Circle one that has the higher ionization energy. Strontium, Sr, or tin, Sn. That's okay. Strontium or tin. You got it, Steph? What do you think? Which one's going to have the higher ionization energy? Which one's going to be harder to pull an electron off of? Tin, yeah. Tin is going to be a harder atom to pull an electron off because tin would rather gain electrons than lose them. Okay, let me give you another pair here. Silicone and magnesium. Silicone and magnesium. Jot them down, circle them with the higher ionization energy. Okay, what do you think, Daniel? Okay. Yeah, silicone is closer to the noble gases. The further you move across the period, the closer you get to the noble gases, the higher that ionization energy is. Now, what did we say? Let's just go back and think about this for a second. What did we say about what happens to atomic radius as we go across the period? It decreases. Huh, that's interesting. That's interesting. So they're getting smaller, they're getting those outer electrons pulled in more tightly, and their ionization energy increases. Huh, how odd. Okay, so what about lithium or oxygen? Grant, what do you think?
Oxygen.
Oxygen. Higher ionization energy. Now let me ask you this. Of those two that I just mentioned, which one would have the smaller atomic radius? Oxygen. Odd. What about calcium or arsenic? Calcium atomic number 20, arsenic atomic number 33. Which one's going to have the higher ionization energy? Who have I not heard from yet this morning? Arsenic's going to have higher ionization energy. Which one's going to have a smaller atomic radius? Arsenic. Are you noticing a trend with atomic radius and ionization energy? What trend are you noticing?
That when the energy level increases,
Okay, when the ionization energy is higher,
the radius.
yeah. Things that have a higher ionization. As ionization energy increases, atomic radius decreases. Why would that be? What did we say caused those smaller radii yesterday? The nucleus is pulling in those outer electrons and holding onto them tightly and pulling that atom in and condensing it. Well, if it's pulling on them really tightly, guess what? It's harder to pull an electron off. Okay, so now let's talk about trends in groups. Okay, here, look at this. here's a graph of atomic radius and ionization energy. So that bottom line is the atomic radius. Bottom line is atomic radius, right? Very pale little line. I don't know, you can see it better on your notes actually. Okay. This line here is atomic radius. This line here is ionization energy. So let me ask you this. What do you think, well first of all, what trends do you notice in ionization energy?
It goes up and it sharply decreases and goes slowly
Okay,
back up.
so we have this whole set of these jagged stair steps where it goes up and then boom. The next ionization energy is very, very low, and then it goes up again, and then boom, and then up again, and then boom, and then up again, and boom. What do you think that represents on the periodic table? And if you look real carefully, I don't know how obvious it is on your notes, these are labeled along the bottom. So in what order do you think they're showing those? It's across a period in the main group. So we go hydrogen, helium. Helium's a noble gas, right? Back to, what's element number 3? Lithium. Then we go up to beryllium. And there's a little bit of a hiccup around boron, for reasons we're not even going to go into. We go up to carbon, nitrogen, and oxygen. Again, a little hiccup for reasons we're not going to go into. Fluorine, and this is what?
Neon.
Neon. So, yes ma'am. Oh, you were answering that? Okay. So let me ask you this. Jot this down on your paper, don't shout it out. If this is neon, what do you think this high spot here represents? This is neon. So this is helium, this is neon. What do you think that high point right there represents? Jot it down. What do you think? Argon. Argon! Does anybody else have argon written down? Okay. Why do you think that? They have high ionization energies, yeah. So for each one of these represents a period going across the main group. The highest ionization energy in each group is going to be the noble gas, right? So what do you think that second highest ionization energy is? It'd be the halogen, which is group 17, what comes right before the noble gases. The lowest ionization energy in each period is going to be what? It's going to be group 1. They're more than happy to get rid of an electron. Now, if we look at atomic radius here, let me change the color on that line. Notice that when atomic radius goes up, ionization energy goes down. As ionization energy is increasing, what's happening to atomic radius? Decreasing. Atomic radius shoots up. What does that second peak on atomic radius represent?
Sodium.
Yeah, it's a group 1 element. The group 1 elements are going to have the largest radius in their period. They have low ionization energy. They're relatively fluffy compared to the halogens or the noble gases. Okay? I like this visual because I think it does a good job of showing that relationship, that these things are what proportional. There are 2 options, directly proportional, inversely proportional. Which are these? It'd be inverse. Yeah, this is an inverse relationship. when atomic radius goes up, ionization energy goes down, and vice versa. So it's an inverse relationship.
Why
in
is
the
there a
field.
little point on top of sulfur then?
Why is there a little point on top of
Yeah, why is it the atomic radius?
there? It's one of those hiccups.
Oh.
So, and it has to do with hybridization, I believe. Okay. Now, we pull off that first electron, that's our ionization energy, initial ionization energy. Can we, in some cases, pull off more than one electron? Yeah. There are things that lose more than one electron. Well, we have second ionization energy, third ionization energy, fourth ionization energy, if we're pulling off more than one electron. And for each ionization energy, it's a little bit higher. It's a little bit higher, it's a little bit higher. Let's draw this and see if we can figure out why. So let's take boron, our friend boron. So boron has how many protons? 5 protons. So 1, 2, 3, 4, 5 protons in the nucleus. Then it's got 2 electrons on the first energy level. How many more electrons does it start off with? 3 more. So they're all going to go on the next energy level. Okay. So when we pluck off, so right now we have 5 protons pulling on 5 electrons, right? Okay. And boron's got 3 on that outer level, so it's relatively compact. When we get rid of 1 electron, so now we've gone from boron to boron 1+, we now have an ion. Once we have a positive ion, a cation ion, how many protons are there pulling on how many electrons? 5 protons pulling on how many electrons? 4. This is like playing a game of tug of war where somebody's removing people from one team. It gets harder and harder and harder to pull off each electron. Now, let's look at the noble gas notation for boron. Boron's noble gas notation would be helium 2s2 2p1. So at the point where, so that's just plain old boron. When we get to boron 1+, that's terrible. We're now at boron looking like He2s2. Everybody wants to be like a what? Like a noble gas. So boron will give up 2 more electrons. Well, if we pull off 1 more electron, we now have boron 2+. Boron 2+ has this noble gas configuration. Okay. Helium 2s1. Boron will give up 1 more electron. But at this point, you've got 5 protons pulling on just 3 electrons. This is not a fair tug of war. So the ionization energy is huge. This is high-level ionization energy. When we get rid of that last electron, and we make this boron 3+, boron 3+ now has the exact same electron configuration as helium, its nearest noble gas. You want to take a guess what happens to the ionization energy? It goes through the roof. No one's going to give up electrons when they're just like a noble gas. At this point, I mean, in theory you could do it, but the ionization energy is so high, it's just not going to happen. It's just not going to happen.